Come back. So this was the last discussion we had on earthquake prediction part, and as I mentioned that there is no robust method till date developed to forecast the earthquake. There are studies which are done based on the paleoseismic investigations. That is what we call to identify the ancient earthquakes from geological records and surface morphology. At the same time, the additional we can see the methodology which has been used is global positioning system, GPS, that can tell us about the ongoing deformation, and if any area is under strain and that area is accumulating strain, because the sudden release of earthquake, sudden release of energy is basically the earthquake we define. So, if you have the locations identified of active faults, then you can have the GPS stations which can tell that how fast the deformation is taking place along that weak zone. So, for example, this is a theory which we call elastic rebound theory, and as we know and understand that most of the material in the earth crust are elastic, they have their particular elasticity and threshold limit of the elasticity. Now, rocks near the, for example, if you take this as an fault trace, you have okay. So this has been identified based on this the landform investigations or the studies and located in the field on ground. So you can monitor that fault, provided that fault you categorize as an active fault, which can produce and have the capability of producing earthquake in future and had produced the earthquakes in past. Okay. So one can monitor the slip, one can monitor the ongoing deformation. So here the best example which has been given is the man-made structure, that is the artificial fence, which over the time gets deformed because of the accumulation of energy or the strain, and then there will be some slip, but it will be sort of an it will remain sticked. Okay, it will not get the displacement. Okay, so initially it will deform, so it will sort of an waved up, or we can say the warping will be seen, and or some displacement, but not slip. Okay, so you have that deformation. Better to call deformation rather than slip or displacement. Okay, but finally after the threshold limit, as we have seen in the beginning, that you have the clear cut deformation pattern in a strain and stress graph, where at particular like point you will have a displacement, that is a fracture. So the energy will be released and that will result into the earthquake, as well as the displacement will be seen, and then after the energy is released, again that area will show some sort of an rebound, and then we will see a sort of that area might be coming back, and you have a sort of a residual displacement which has been left out. So this is one of the best example which can be studied based on close monitoring, and if you have GPS stations you can do that actually. So this is another example of the fault which is having a right lateral displacement, and you are having a slip over the time. So this is the portion of the deformation. So you will be able to see if you have, for example, GPS station sitting here, not very close but away, but in some cases people have put very close also, and they have been able to get the success. So because just GPS stations are recording the coordinates 24/7 and in real time, so you will get this coordinate changes in the coordinates, so that can help in identifying the deformation. And finally what you see is the slip. Okay, and that is your earthquake. Now this was a very well known example which came across during an earthquake of 1906, that is San Francisco earthquake along the San Andreas fault system. And so this shows that there was a clear-cut displacement of this fence, and fault passes through this yellow dotted line. Okay, and this was the offset which they were able to see along the San Andreas fault system. So again, this is an right lateral because this block is moving towards us, and this is away from us. Okay. Now this experiment was been done, as I told, that if you know the fault trace, which has been shown in the left hand side figure, this is a fault trace with the black dashed line, which has been your San Andreas fault system, and the size, or you can say the scale, you can gather based on the car which is standing here. Okay. Now the numbers which have been seen here along this line, okay, from 1 to 15, for example, they are all GPS stations which they have put. Okay. Now the idea was that to understand that how fast the stations are moving close to the fault and away from the fault. Okay. So that what they have tried to identify, and then what they observed was that the stations which are away from the fault line have moved bit more in terms of their position, okay, initial position, and that what has been shown here, that the maximum displacement which they observed was 905 millimeter, and that what they were able to see, and close to the fault, the displacement or the movement was minimal actually. So if we consider that this is a typical cycle which an earthquake will follow on a particular fault, then one should get this type of sequence. Okay, that what we call the sequence of stress development over the time. Okay, so you have the time which has been taken up here to develop the stress, or the energy is stored, and then you have a release. Okay, so these are all your earthquakes. Okay, so you can say earthquake 1, earthquake 2, and so on. Okay, now whether this is, how far this is true, if we say that okay fine, this is going to be the same pattern which you are going to observe, then one can predict the next earthquake, for example. Okay, so this will be the next earthquake which will take place, and you can predict the time. Okay, since we are talking about the prediction, but in nature this never happens. Okay, that what we have learned from the studies which we have carried out from Himalaya. This is what we call the recurrence interval. What is the reoccurrence of the same event. Okay, and whether the magnitude remains the same, whether the displacement remains the same, that is not systematic. Okay, so this is what, as I told, that this we have learned from our experience in studying the paleo earthquakes in Himalaya. Okay, because the reason behind this is very simple, is that the stress pattern or the strength of the rocks, okay, through which the fault displaces the succession, changes over the time. It reduces, it will not remains the same. Okay, and at the same time there are few other regions which have been learned from, even from the Sumatra region, that the stress can trigger or the sudden release of the stress can trigger a release of stress which has already been available on the nearby faults. Okay, so the systematic pattern never comes true. In some cases maybe, but not always. Okay, so this type of prediction is again and sort of it may be not fruitful, actually, we can say. Now another exercise which the scientific group does is your measurements of the slip, okay, over an year. Okay, that is what we call the slip rates. Okay, and this slip rates, okay, estimation of the slip rates are again done by either the geological signatures or the evidence, or it has been done based on the GPS studies. Okay. So, once you have identified the fault lines, that what I have been mentioning is the active fault. So, once you have identified this, which is very much important, then you can select the location of GPS stations. Okay. And this exercise we have done in Himalayas for Himachal Pradesh, where we have first identified the active faults, and then we decided the locations of the GPS sites. Okay. And these are the all permanent GPS stations, okay, which keep on recording the coordinates 24/7. So, this exercise, this map is from US, and it shows in this orange lines are all your fault lines, and it forms a fault system of what we call San Andreas fault system. And if you carefully look at it, then that this doesn't have the same slip. Okay. So, you have differential distribution, we can say, on the slip, and even each portion of the fault, okay, where they have named as different faults. Okay. So, there is a San Andreas, and then you have Hayward faults, and so on. Okay. So, they are not slipping at the same rate. Okay. They have different rate. Okay. So, and this Hayward fault and further north, that fault is also not slipping at the same rate. Okay. Where the highest one, if you see, is the northern portion of the San Andreas fault system. It's 24 millimeter per year. Okay. Now, this area will have potential to trigger an earthquake quicker than, or maybe the time period will be lesser as compared to the other areas where you are having the Rogers Creek fault and the Hayward fault, okay, which is 6 millimeter, and even the San Giorgio fault is almost 3 to 4 millimeter per year, which will take long time to trigger a large magnitude earthquake. Okay. So, higher the slip rate, chances of having your earthquake recurrence, okay, will be shorter actually, and that increases the hazard in that area. Okay. So, this type of studies are extremely important in any seismically active regions. Okay. For example, we have Himalaya, which is in one of the most seismically active region in the world. Okay. So, we need to have this type of data based on the geological, we can say, plus geomorphological. So, this evidence is required, okay, and then you have the GPS measurements. So, based on this, one can talk about the slip rates. Okay. To some extent, the geological signatures may not give the most robust slip rates, but the GPS can help. Okay. So, you need to have more data point in terms of the geological slip rates if you are using the geological evidence to calculate the slip rates. Okay. And but since GPS will have multiple locations that can add to your accuracy, more accuracy in terms of the slip rate calculation. Okay. Now, one example I will try to show you that there are faults, and there will be, like we can say that there may be faults in the fault system, like for example in Himalayas and all that, that few of the faults might be creeping. Okay. They are not locked. Okay. So, locking basically is like if you have a fault here, for example, then we can say the locking is that they will just show the deformation. Okay. So, they will be having a sort of a deformation, but they will not slip. Okay. But there are, and then finally when they slip, this portion is displaced, then there will be an earthquake. But some faults will keep creeping, like for example, what we see in the landslides. Okay, that slowly the landmass or the material sitting on the slope will creep slowly. Okay, the same way this faults also creep along the fault, and you have the creeping which is going on very slowly. Okay, like very slow creeping is going on. Now this is one of the classical example which the US people have, is from the Hayward's fault, which is which they identified that it creeps actually. Okay. Now how they observed this was that they were these are the houses which are sitting on or close to these Hayward fault line. Okay. So they observed over the time that their subsurface utilities, okay, either it is a gas line or the water pipeline or sewer line, okay, and also on the roads and all that, okay, and the walls of their houses and all that, they observe cracks, okay, and then finally they are broken. So that and even the pedestrian path, okay, clearly shows some sort of an bending, okay, which you can see here, that you have no one will construct like this provided there is some sort of an issues in terms of the area. Okay, but this bend is nothing to do with the obstructions in the construction or something, but this is related to your movement. Okay, so this part actually you can see that it is showing that it has gone like this, okay, and this has moved like this. Okay, so the fault passes through this one. Okay, another example that they see a very typical what we call the riddle fractures on ground. Okay, and this cracks, okay, what you are seeing is nothing to do with the poor quality of the construction of road. This is related to a typical deformation which takes place in a lateral displacement. Okay. So again the close up, if you see over here, I can show you this one. Here you see there is a clear cut displacement. What they do is that they very well understand that this is, now they have it has been proven by detailed study that this fault creeps. Okay. So immediate action what they have done is that they have stopped allowing any further construction or in this area in terms of the houses or any lifeline structures. And then second is that they understand that this fault is creeping. So they have come up with an alternative of very flexible material which should be used for your utilities. Okay. So at least for longer span of time they will have that flexibility available in their utilities. Okay. So no immediate breakdown in the region, but they will allow that over the time, then finally when they reach the maximum limit they replace it. Okay. And they keep on repairing this the pedestrian path and the corners of the roads, keeping in mind that now it is maximum, so let us repair it and make it. Same thing they observed, and they were unable to figure it out that why there were derailments in this area, okay, after few years in of the railways. Okay. So they found that this is again and a part of the San Andreas fault system, and the Hayward fault is creeping. So what best they did was that they usually have the tracks, new tracks has been put on the next in the side areas. Okay, and then they sort of they remove this, or maybe they are the limit of the bending if they come across, which can result into the derailments. So they put it aside and they put the rail traffic on the new tracks which have been constructed next to it. Okay. So this they keep on doing. So next time, like if you can see clearly there is a clear cut bending here. Okay, in this track. Okay. So now they will put the the train on this new track. Okay. And then they will repair this, and then the alternative has been done, okay, to safeguard. So, what lesson we learn from this is that since they knew, or they came to know, that this is the level of hazard which they can experience. Okay. So, it is better to take precautions. Okay. So, a lot of risk part has been reduced in this. Okay. So, that is how the other parameters also can be taken into consideration, and one can use this to reduce the hazard posed by such activities. Okay. So, there is another example of 2004 and 2006, the amount of displacement which one can look at along the San Andreas fault system. Even people are staying with that, but now, as I told, that they have been asked not to put their houses on this particular fault line. Okay. But they will keep experiencing such type of displacements and destruction. Okay. So, and as we all know very well that this Northern American plate is also one of the most seismically active region in the world, and you have one of the dangerous fault on this planet is your San Andreas fault system. So, they know that they are sitting on a giant crack in the earth, okay, crust, and that is your San Andreas fault system. And even the fault passes through or under their city. Okay. So, that is also they know, but they have tried to come up with the solutions, okay, to minimize the damage. Okay. So, this is an example of Seattle, where they know that there is a Seattle fault which crosses through the fault line. And similar example, if we see, is from your Kangra Valley fault. Okay. The Kangra Valley fault, which we identified in 2015, it passes through the valley, okay, where people were unaware about even after 100 years, that where the fault lies. Okay. 100 years, why I am saying that? Because 1905 was the major earthquake in that area. Okay. So, we will come to that part also as we move more in detail about this region. Okay. Now, GPS not only helps in identifying the strain development at the local scale, but on the regional scale also. Okay. So, these are some vectors which you see of which are plotted from different GPS locations. Each vector is your location of GPS station, okay, which shows clearly that the deformation which is going on between the Tibetan plate and the Indian plate is forcing the Tibetan plateau squeezing out towards southeast. Okay. It is moving towards southeast. So, these are the vectors which shows that this portion has been, like you can say that it has been sandwiched and been pushed out in the western and southeast direction. Okay. So, this is another part which one can use GPS to identify. Now, coming back again to the prediction part, the earthquake prediction has had few successes. Okay. It is not that completely we can say that we do not have any success, but there were few successes and what we call based on the earthquake precursors. Okay. So, people try to look at the animal behavior, but this is again a very short term prediction. Okay. This is immediately after, or you can say that during the passage of the seismic waves through the crust, the upper portion of the crust, the different frequencies which the animal can gather and observe. Okay. So, based on that, people have worked unusual electrical signal, because yes, a lot of changes people have been working on this, that there will be change in the total electron counts at the in the atmospheric portion. Okay. And that can result into your unusual electrical signals, and then many large earthquakes are preceded by smaller swarm of earthquakes, I would say. So if the seismologists keep on monitoring very particularly in the area, then one can also predict that. Okay. Now, Chinese authorities used series of foreshocks, okay, because we say the main shock is the main earthquake where the maximum energy has been released, but before the main shock there are foreshocks, okay, and then after the main shock there are aftershocks, what we call. Okay. So, in 1975 Haitian earthquake was been predicted, okay. A lot of people will be saved from that. Okay. So, we will stop here and we will continue in the next lecture talking more about the earthquakes. Thank you so much. Namaskar.